In this video, we'll discuss the area of polygons. Now, much of what we think about area can be built through two principles, the additivity principle and the moving principle. The additivity principle says that if we take a large shape and divide it into smaller shapes that have no overlaps, the sum of those smaller shapes will be equal to the area of the larger shape. So let's look at an example here. Say we have this basement layout and we want to know how many 1 square foot tiles a contractor will need to actually cover this basement floor. And we're assuming that each of those angles are right angles. So with the additivity principle, I can look at that and say, I don't know what that is as a general shape, but I can split this into smaller shapes that I do know, such as rectangles. So if I draw a line here, I can now find the area of this small rectangle and then this large rectangle. And this small rectangle would be 6 by 7, which is 42 square feet. Whereas this large one here would be 15 by 18, which would be 270 square feet. So combined, when I add them together, that would give us 312 square feet for that space. I also could have taken and drawn the line horizontally across here and looked at the area of these two rectangles. If I did this, again, this would be 6 by 22, which is 132 square feet. And then this would have been 15 by 12 or 12 by 15, which is 180 square feet. And when added together, again, those two values will be 312 square feet, which means since we're using 1 square foot tiles, it will take 312 tiles to complete the job. Now, it's important to recognize there's a third way we can think about additivity principle, which is we can look at subtraction. So if we take and fill in that empty space there and look and say, okay, now we have this large rectangle and we can subtract out the space that doesn't exist in the actual shape, which is a small rectangle. So the large area would be 18 feet by 22 feet, which is 396 square feet. That small rectangle is that 7 by 12, which is 84 square feet. And if I subtract 396 minus 84, I will get 312 square feet there as well. So those are all forms of how we can use the additivity principle. The other principle is called the moving principle. So sometimes we may have odd shapes, but if we take parts of them and move them without stretching them, we can make shapes that are known and find their areas. So say we have this shape here. We can't find the area as it is, but what we recognize is that if we draw these lines here, we can cut off this top piece and then it will shift and move down into this bottom piece, and that will create a corresponding rectangle. And we can find the area of the rectangle because that would be 22 by 30, which would be 660 square feet. So that's the concept of the moving principle, is that we would cut pieces off and move them. We don't stretch them, but we can rotate them and we can translate them and reflect them. Now let's look at some actual shapes that we can use then to help us if we ever have to use those. One of those being the area of a triangle. And the area of a triangle is 1/2 the base times the height. Now the key to remember here is that the base does not mean bottom. The base is the chosen side of the triangle we want to make the base. Then the height corresponds to that base because it has to be the perpendicular distance to the opposite vertex. So when I look at this triangle, I would say I don't have a bottom side. I could choose any side to be the base, but I want to choose a side that makes the most sense. And in this case, I want one that I can count on the grid easily. In that case, my easiest side to count is HG because I can count 1, 2, 3, 4 units. So that means I need the perpendicular distance up to F. So what I can do here is I can think about line F being, or a line going through F, and a line going through HG and say, where's the perpendicular distance? It would be right here. So I can draw that in and say, okay, that's 3 units. That's the height for this triangle. So my area would be 1/2 4 by 3, which would be half of 12, which is 6 square units. Now we can use the moving and additivity principle to think about this as well. So here is a right triangle, and we'll use that because it's a little bit simpler to talk about all 3 methods. Algebraically, we would say this is 1/2 of 3 by 4, which would be half of 12, so this would be 6 square units. Now, if I think about the moving principle, I say, okay, where can I draw a line and cut and rotate a piece? Well, if I take that top half, I cut it, and I rotate it counterclockwise, I can make a rectangle. And I can say, well, what's the area of that rectangle? it's 2 by 3 or 3 by 2, which is 6 units or 6 square units. Now what about the additivity principle? So what we talked about before is the idea that additivity can also be subtraction. And if we take and double the size of this to make a rectangle, we can say, well, I now created a rectangle. The area of that triangle, as can be seen in this image, is half of that rectangle. So half of a 3 by 4 gets us to the half of 12, which is 6 square units. And this is the reason really why we talk about the algebraic formula being 1/2 of base times height. Now let's look at the area of parallelogram, which again is the same as the rectangle, which is base times height. But remember, the base can be any chosen side of the parallelogram, and the height will be the perpendicular distance to the opposite side, just like that of a triangle. So here is parallelogram PQNL, and we want to know what's its area if we think that each of these grid is a square centimeter. So when I look at this, PL is what people may call the bottom, but it's not the easiest to use for the base. My base would be easier to use NL because I can count that on the grid and say that's 5 centimeters. Then what I want is the perpendicular distance to the opposite side. So I'm going to draw those parallel lines again and say, okay, let's go perpendicular to those and say that's 2 centimeters there, so that's my height. So the area of this parallelogram would be 5 centimeters times 2 centimeters, which is 10 square centimeters. So we can think about this also through the 3 different methods as well for parallelogram. Algebraically, if we look at this parallelogram, we could say that this is 4 by 3 because of our base and our height, and that would be 12 square units. If I use the moving principle, I could chop off the left side here, and I can shift it to the right, and I can see that creates a rectangle that is 4 by 3 units, which is 12 square units. And if I think about the additivity principle, I could split this into 3 smaller shapes, 2 triangles and a rectangle. And those 2 triangles will each be 1 by 3, so that's 1/2 of 1 times 3. And then I have my rectangle, which is actually a square, so it's 3 by 3. And then another 1/2, 1 by 3. And I add them all together, and again, I'll end up at 12 square units. So I can use these principles when I'm unsure of what the foundational formula may be for the given shape. Now let's look at the area of a trapezoid. The area of a trapezoid is 1/2 of the sum of the 2 bases times the height. The key to this is that the bases must be the 2 sides that are parallel to one another. So you have to just look and say which 2 sides are parallel. That's base 1 and base 2. And the height's going to be that perpendicular distance between those 2 bases. So say here I have trapezoid DFEK, and the grid is 1 square foot for each of those little squares on the grid. Now when I look at this, I gotta say, well, what 2 sides are parallel to one another? It's FD and EK. And when I look at that, so DF would be 3 feet, because I can count that, and EK is 7 feet, and I can count that as well. And then I say, okay, I need the perpendicular distance, that height. So when I look at the perpendicular distance, I'm going to look from one to the other, since they're already parallel, looking just straight across, that's 4 feet. So now I can plug it into my formula and say 1/2 of 3 plus 7, and then times that by 4. So that's 1/2 of 10 feet times 4 feet, which is going to give me 20 square feet when I multiply those 3 values together. Now again, let's look at the 3 different methods we have here and understand how does this work with each of those methods. Algebraically, if we looked at this, we'd have 1/2 of 3 plus 6, and then times the height, which is 4. And that would give us 1/2 of 36, which is 18. Now, if we wanted to look at this from the moving principle, this is where you have to chop and move things a little bit more at a time and to think about what's going on. So I'm going to split this into 2 pieces, and I would rotate this blue piece to the left, and I'd rotate this red piece to the right. And you could slice and move different ways here to make this work. But when I do that, what I see is I end up with a rectangle that is 2 by 9, which would give us the 18 square units. And if I did the additivity principle, I'd probably split this into 3 shapes. A triangle on the left, a rectangle in the middle, and a triangle on the right. And I'd say then I would have 1/2 of 1 by 4, and then the rectangle will be a 3 by 4, and then this other triangle will be 1/2 of a 2 by 4. And when I add them all together, that'd be 2 plus 12 plus 4, which will give me, again, 18 square units.